We just got done talking about the 7 steps of the scientific method, and uh, a lot of people think that like the eighth step kind of is coming up with a theory. If your book even says it, and I really disagree with what your book says here. I know why it says it, but I disagree. A lot of people think theories are either just a guess or they think theories are totally well proven. I mean, these are complete opposites. How can something be just a guess or just completely well proven? And you already know that I don't like the word proven. And so I'm going to give you another way of thinking about theories that I hope helps you with putting these two ideas together. Like, it kind of is, in some ways, both of those things together. So the actual definition of a theory, the one that I think is the most useful, is it is a collection of hypotheses. It's a whole bunch of ideas that if you take them all together, explain, because that's what hypotheses do, they explain, right? Explain a set of related phenomena. Again, this is a different definition from your textbook, but it's also related. So let's take a closer look at this and understand that there are actually 3 types of theories, according to my world, and according to, I think, the real world. Maybe your book's a little off on this. So the first one is the untested theory. This is an idea where you attempt to explain this wide set of phenomenon, but you haven't actually tested it yet. And this is actually how a lot of theories start. You have this idea about this big picture thing, and you come up with all of these ways that explain it. Maybe if you're doing physics, you're coming up with a bunch of equations that explain the relationship, or in biology, maybe you're trying to explain how species change over time. That might be an untested theory. But usually untested theories don't stay untested for long. Usually they get tested pretty quickly. Upon being tested, there's 2 things that could happen to that theory. It could be rejected, or it could be so well supported that we say it's embedded. Rejected theories are theories that are not consistent with evidence. So a long time ago, when people were trying to explain how species change over time, some guy said, well, maybe they just need to change, and that need of changing, that's what drives this. This guy's name was Lamarck, and we'll talk about him in chapter 12. But there was no evidence for this. Like, just because you need something doesn't mean it's going to happen. So we reject that theory. On the other hand, Darwin's theory of evolution has been supported by the overwhelming weight of evidence. It's widely accepted, and you can use it to generalize to any example of evolution, not just the ones that he specifically used in writing about it. So that's embedded theories, and there's lots of embedded theories. We tend to spend most of our time in the textbook talking about embedded theories. That's why your book talks about the theories being supported by the overwhelming weight of evidence and why they accept it, and it has generalization. And if I go back a slide where we were talking about how theories are just a guess versus, oh, they're quote unquote proven to be true, well, these subtypes of theories really deal with that. We can have untested theories, or we can have embedded theories, but you can also leave space for rejecting theories, just so long as you keep in mind the definition. This broad definition is a collection of hypotheses that, taken together, explain a set of related phenomenon. Then you really, really will understand what a theory is. Let's go through an example of a theory. This is germ theory, and with germ theory, there's 3 broad ideas. Certain diseases called infectious diseases are caused by microorganisms. They are transferred from one individual to the next, and when the microorganisms reproduce and their population rises within a person, that's the disease. So that's germ theory. Notice how broad this is. Notice how it applies to any general disease where you catch it from another person or from another organism, and notice that that we have a lot of evidence for germ theory. So germ theory is an embedded theory. It's got tons of evidence for it. It's the kind of theory your book talks about. There are lots of theories out there, lots of embedded theories, but there's also some untested theories out there, and maybe you're familiar with some of them. One of my favorite untested theory, not in biology, because biology has mostly tested all of its theories, is from physics, and that's string theory. And so in physics, they're trying to figure out how everything works together, the universe as well as atoms. They don't really know how that works, and so they're trying to come up with a theory. It's not really tested, so it can't be rejected yet, but it also isn't embedded, so it's a untested theory. The rest of our time we're going to spend answering this big question, at least for most of it. How can you tell if something has or lacks scientific validity? Remember, we just went through the whole scientific method, and the whole idea here was to get through this idea that you are already a scientist and that you need to be able to use the techniques that we've learned to apply in your everyday life. But there are some other things that we need to think about as well, including really getting a little understanding of statistics. There's something called the placebo effect, how to design a good experiment. So we talked about things there, but we're going to expand on that a little bit. Knowing that biases creep in, avoiding anecdotes are stories, and then recognizing pseudoscience, and I'll have a little bit more on statistics, I think. So starting here out with statistics, how can you tell? You need to understand basic statistics. So on average, we know that human males, are taller than human females. But just because on average we see that human males are taller than human females, that doesn't mean that all males are taller than all females. And so you kind of have to understand that. The other really key thing for statistics is that you have to kind of be on the lookout for how individuals use data by kind of cherry picking data. They're selectively using data. It's really important not to get fooled by cherry picking data. So again, the average male is taller than the average female, but we do know that there are males that are shorter than females, or females that are taller than males. So we don't want to use selectively used data. We want to use all the data that's available. You also have to be aware of something called the placebo effect. This placebo effect is one of the most powerful phenomena in science. So it's the idea of the sugar pill. You take this pill and you think it has an effect when really it actually might be having an effect, but the effect is not medical. I mean, it's not due to the pill itself. It's due to the way that you think is going to happen, the things that you think are going to happen because you've taken that pill. So the placebo effect is really powerful. An example that your book gives is that there was actually a study about the placebo effect. Two groups were given the same sugar pill, but the first group was told that the sugar pill would act as a stimulant. It would actually increase their heart rate, and it would increase their blood pressure. For the same exact pill, they told the second group that this pill would actually act as a depressant. It would calm you down, it would decrease your heart rate, and decrease your blood pressure. What do you think happened? The placebo effect is so strong that the first group had the stimulatory effect, and the second group had the depressant effect. So you've got to be really aware that maybe you're buying something on the market that says it'll have a positive effect, but it could just be a placebo effect. Does that mean you shouldn't take it? And my answer is no. If this placebo is having an effect that you want, and if you can afford it and it's not doing you any harm, then it might be okay to be taking it. Just be aware that this effect happens, the placebo effect. Also, be aware that in a well-designed experiment, the placebo effect is taken into consideration. So you might have your control group be given a placebo, and that way you know that the effect of just taking the pill isn't what's causing the effect that you're seeing. So it's really important. When you're designing an experiment, there's a lot of things that should go into it. When you're reading about an experiment, there's a lot of things that should go into it. Like that experiment should include a lot of people. Though the experiment should be repeatable. The people that go into the experiment should be randomized. Don't put the first half in group A and the second half in group B. Randomize them whenever it's possible. You should have control groups and experimental groups. And finally, it should be peer reviewed. So if we take a look at this is out of your textbook. A study was done on 1 or 2 people and found that that it might reverse AIDS. That doesn't fall under, like, you shouldn't believe that necessarily. It might be maybe hopeful, but it's not good enough. You want it to be large and you want it to be repeatable. And it turns out that when they repeated it, they did not find any effect of that drug on HIV/AIDS. So we don't know what happened when it was done, when it was reported on the news, but when it's peer evaluated, when it's put into a scientific journal, you have much better chance that the data are reliable. So just kind of keep that in mind. Even if you have a scientific study, it's not always possible to have the best kind of scientific study. For example, you can't always take a group of people and say, hey, you're gonna be exposed to radiation and you're not. Like, that's not ethical. And so sometimes you can have a good study that doesn't have a control group necessarily. And the way that they handle that is they look for a group of humans, usually, and they put them into this thing called an epidemiological study. This is a study that looks at a large subset, but they don't have randomized groups. So they take this cohort of people, oh, this group of people has been exposed to radiation? I'm so sorry, but let's measure how much cancer comes up. And we've got a group that was never exposed to radiation. Okay, let's see how much cancer comes up. So we're not randomizing the people. We're just looking at the groups that were formed for you by nature or by accidents or whatever. The thing about epidemiological studies using cohorts or groups is that you really can't draw conclusions about causation. Only correlations. So you could say, well, there were more cancers in the group that was exposed to radiation, so there's a correlation there. You can't say just from that study that the radiation caused the cancer. You would need to have a better, well-designed experiment where you actually, maybe you use rats or something along those lines, and literally randomize them and expose them to different levels. A good scientific study would be double-blind. And double-blind just means that the person who's doing the experiment and the subject, neither one of them knows what exactly is being administered. So, so in the placebo situation, maybe you don't know whether you were given the placebo or their actual medicine. Neither does the person who's doing the administration. Some secretary someplace knows, but the person who's giving you the pill, they don't know. a really interesting version of this is described in your book with this horse, Clever Hans. Clever Hans, everybody thought could count. They were fooled into thinking that this horse could count because the test was not double blind. The trainer got Clever Hans to count by hitting his hoof on the ground. Well, Clever Hans was a clever horse. He could read his trainer's body language. And the body language, he would shift his weight, and Clever Hans would stop counting. And all the people in the crowd, they thought, oh, this is the smartest horse ever, it could count. To make this a true double-blind study, the trainer would have to be elsewhere, so that neither the crowd nor the horse was getting any other signals. How can you tell if something has or lacks scientific validity? You want to make sure that the people conducting the experiments are not biased towards or against that experiment. A lot of times in industry, you get people designing experiments that they're hoping will show that this drug works, right? That's kind of a bias. So a lot of people in industry will ask scientists that are outside of that industry to run independent studies. I think that the example that your book on biases gives is really interesting because all people have biases. And a lot of them are not conscious biases. They're subconscious biases. They're ingrained biases. And so what this one group did was they're trying to figure out why women in science don't publish as much as men in science. And so what they did was they had this group of peer reviewers who knew the sex of the author, and they had this other group that were not allowed to know the sex of the author. And so they basically hid the names of the author. And so what happened was that in the group where they knew the sex of the author, they only allowed to be published 23.7% of the papers that were submitted. But when they didn't know it, 31.6% of those females got published. And so even scientists have biases, and the more we can address those subconscious biases, the stronger the science is. I also said that we should avoid anecdotes. And so anecdote is a story. It's a plausible but untested story that somehow sees correlations between two things. And so they tell you the story. And a really powerful example of a story that has been told over and over and over again is the story of autism. Back in the 1990s, there was a paper published. It was a very poorly done paper, but it said that there was a correlation between vaccinations, especially the MMR vaccination, and autism rates. And so this is an example of what you might see here. Like here's the autism rates in two different countries. This is the UK, actually this is in the United States, and we see that we have an increase, a really sudden increase in the 1970s. And it was in the 1970s that kids really started getting vaccinated by the MMR vaccines. And so we see this sharp increase in two separate countries, the number of autism rates increasing with the number of MMR vaccinations. And so, like, that makes sense, right? Why aren't these causing each other? And so what happened was Japan, basically in the 90s, the government was so worried about the MMR vaccines causing autism that they basically banned the MMR vaccine. And so here's the number of vaccinations that went from a really high number to basically zero in Japan. And what we have here are autism rates in Japan. And there's just three different numbers of autism rates, just so you know. But basically what you can see here, and the green line is the most important one, is that the rates of autism did not change at all in the same time frame where the MMR vaccine went to 0. And in fact, if you look at the blue line, which is just it's a absolute number of oops, sorry about that, absolute number of cases of autism, that actually also did not increase. So vaccines don't cause autism. I mean, it looked like it might have, but when the data came in, it didn't. So there's something else going on there. And we'll talk a little bit more about that again in a second. So how can you tell if something has or lacks scientific validity? The last one that we're really going to spend time on is pseudoscience. We'll swing back around to some of those other topics that we've already covered again, just to reinforce a few things. But pseudoscience is the bane of any shopper's existence, because what you see on a lot of products that you're buying is that there are these scientific sounding claims. Oh, it will increase your immunity. So they use these scientific sounding terms, and they do it because they want your money, and there's no actual evidence. The only way that you can recognize pseudoscience is to be skeptical and to do your research, to be, in other words, to have scientific literacy. If you don't have scientific literacy, and if you're not skeptical, you will be throwing away thousands of dollars on, Cocoa Puffs because it says it improves your kid's immunity. So be really, really cautious and careful. Again, pseudoscience is scientific sounding, but not actually scientific. So going back to graphs just really quickly, if a graph can be misleading, so you can't just rely on graphs. Graphs can have misleading scales, or they can have incomplete information, or they can hide assumptions, or maybe you don't know where the data came from, right? This is like a summary of all these things that we've already been talking about. So you can't just rely on a graph to tell you these things. Coming back to the graphs that we've already talked about, right? We talked about height graphs, and here's a great example of a couple that violate that assumption of well, males are taller than females. You have to be careful on drawing conclusions when your data are limited. But when the data are good, it's useful to use that information to actually make your wise decisions. So if you have a textbook and you've got some data that says, well, people who use their textbook score better on average than students who don't use their textbook, and that's interesting, but maybe that's being sold to you by the textbook company, right? So you want to make sure that that you're fully understanding where these data are coming from and how accurate their conclusions are. I already mentioned about correlation, and we already talked about how correlation was not causation. So I thought it might be fun to look at a couple of graphs and see how they're examples of correlation, and some of them are good and some of them are not good, but none of them are necessarily in and of themselves causation. You need other information to figure out causation. So let's take a look at a couple of graphs. This one is a graph of how sour cream sales correlates with deaths from motorcycle accidents, and it's a really good correlation. Look at that. It goes up, and then there goes the decrease in sour cream sales, and that's correlated with a decrease in motors. This is ridiculous. I mean, you kind of intuitively know this is ridiculous. How in the world would these things, when sour cream sales cause decreases in motorcycle accidents? Well, it doesn't. Remember, correlation is not causation. So this is an example of a bad correlation. I mean, it looks really good, but it's not a causation. Here's an example of how carbon dioxide rates and temperature rates over 800,000 years are correlated to each other. And that's really important. We'll talk about this when we get into some later chapters. They are correlated with each other, but just because they're correlated with each other doesn't mean that they cause each other. We would want some additional data. And luckily for us, we actually have additional data where they've put carbon dioxide in controlled locations and measure the temperature changes. And sure enough, like, we can see the causal relationship. We can also see that it has a correlational relationship. We just happen to know, because we did additional experiments, that they are, in fact, a causal relationship as well. The graph alone is not enough to know that. You've got to have additional experiments. And here's one on autism and organic food sales. So you can see that's a very tight correlation, organic food sales going up, autism going up. Does that mean that autism is caused by increasing consumption of organic foods? And I mean, no, it's not. We will talk eventually about what we think are causing autism, but it's not organic food and it's not vaccinations. So don't be fooled by data that you see like this. Okay, our last topic are what is life, and we're going to try to define that and kind of make some predictions about what we're going to be thinking about in the future of this semester. And so let me start out by giving you these 6 things that are shared by all organisms and are characteristic of living systems. They are complex, and they are made of more than one cell. They use energy to perform work. They respond to their environment. They are able to regulate themselves and maintain themselves as they are. And they grow, develop, and reproduce. Finally, they experience evolution with modification over time. So those are the characteristics of life, and that leads us into thinking about what we're going to be covering over the course of this semester. And we are going to be talking about almost every single one of these topics. So there's 2 main themes in biology. That's organization and evolution. Those are the 2 things that biology is united around. Within those 2, there's 4 kind of areas, and that's really nice because your book is actually divided into 4 main sections. The first section, we'll talk about chemicals, chemistry, we'll talk about cells, a little bit about energy, although we don't do photosynthesis and cellular respiration in detail. We hit that again later. The next is genetics, evolution, behavior. Then we have diversity of life. And then finally, we have ecology and the environment and how we are linked to those things. So, so that's what you should be looking forward to in the course of this semester. I look forward to seeing you in class and talking about these things and getting some deeper learning and deeper understanding of what I've just lectured to you about. See you in class.